So yeah, the talk is Java must be faster, and we're going to focus in on the vector API from the Panama project. So I'm Ben. That's what I looked like 5 years ago. That's my handle on all the socials and Twitter, but it's burning up, so maybe not Twitter anymore. And my team is hiring, and Elastic is hiring. So if you know Java and you want to work in a Java software stack, we are looking for folks. And if you're an expert in information retrieval, we are definitely looking for you as well. So yeah, help us find what other people are looking for. So I'm going to go over what SIMD is. And you may have heard that computers are just context switching machines, and they don't really ever do a thing in parallel. And well, that's not exactly true. SIMD allows for true parallelism. So you have an instruction pool that gets loaded into what they call a vector unit, which has a specific bit size, and it does a single instruction. So by instruction, I mean something simple, like simple math, or it can be something complicated, like some very complex linear algebra stuff that maybe you learned about in college and forgot about. It can have multiple, and dimensions are by bit size. So everybody knows about value types and how an integer is bigger than a short, bigger than a char. So how many of those you can fit in a vector type is determined by the bit width or the bit size in your vector unit. Threw a lot of terms at you. You can talk to me about it later. And there's no threads. It's all parallel, all natural. So what's actually happening, and is it useful? So it's true parallelism, and it's a single instruction. Single instruction does not sound very useful. My programs do lots of things. But let's think about it like this. We have 4 floats and 128 bits. That means we can do 4 things at once. Adding 2 floats together and getting an answer is garbage. It's slow. Nobody wants to do that. We want to have 4 floats added together at the same time and get 4 answers at the same time. That is much faster. I really had to fight against doing a lot more animations. That's the only animation, I promise, I think. Some of you may say, but Ben, the hotspot, it's all like auto-vectorized in Java, isn't it? Like it just does all that for me. Well, yeah, it sort of does. Anybody who's worked in Java long enough knows that when you fight with the hotspot compiler to try to make it faster, you have to worry about all sorts of things. You learned about some of those in the JRuby talk and how long they fought with the JVM to make it faster. And there are no promises. But sometimes it does execute SIMD things. This, for instance, will be done in SIMD. It'll take advantage of the bit size of your CPU and do a bunch of integer operations at once, which is pretty cool. But it'll only work up to a certain bit size, which is, I think, 256 is the maximum. And we had that like over a decade ago. So of course, Java's slow at adopting things. Sorry, Java. And there's no such thing as doing this for floating point, which is a lot of the math we do, which is floating point math. Anybody guess why you can't do it with floating point? Yeah, because the floating point arithmetic sucks. So this, as somebody in a math background, these 2 results are the same. Yes? Floating point operations say, no, they are not. You are a fool for thinking that adding things like this should work. It is not associative in floating point math. That means how you do things and in what order will give you different answers. That may surprise you. But the key here is that the JVM wants to be correct and consistent, which means that it will not auto-vectorize or auto-SIMD floating point operations. Because when things get loaded in that vector unit, they can be shuffled around. The additions can happen in different orders. And when you do that in a loop, like we just learned about loops, that can compound over time. And so your accuracy may drop or your answer may change. Now this is only up to like, what, 10 to the negative 6 or something like that. But you know, the JVM wants to be consistent. So Project Panama unlocks this. It allows us to hand roll SIMD operations and say, hey, I know it's not going to be consistent, but I want the speed and it's going to work. All right? OK, sidebar, talk about Lucene. And this is where we found some uses for this. Lucene has been around for like 20-something years. I don't know. I was in grade school. And lots of gasps. So it's a venerable Apache OSS. It's been around for a long time. It's written in Java. It's used by, I have a lot of people here. It's used by Cassandra. It's used by Solar. Used by Wikimedia, where I got all these images. MongoDB uses it. And of course, my company, Elastic, uses it. And you can use it for this various types of searches, like text search. You can do some geographic searches with geopoints, nice math operations. So the anomaly detection guy from earlier, hey, take a look at Apache Lucene maybe, huh? And you can do vector search. And that's what we're going to focus today. Vector search is a new hotness. If you want to know about how the vectors work, how they're made, talk to me afterwards. I only have 10 minutes. So that's what we're focusing on. And why and how does SIMD improve vector search speeds? So in vector search, we can take two arrays and we multiply them together. A simple one is dot product. This code is very familiar and readable. We take a loop and we multiply two things together and we sum them together. Yeah? Very easy. However, since we're not associative, JVM says no. We're going to do every single one iteratively at a time. We will not unroll it. It will not be faster. OK, all right, JVM, then I do this. And this is what it looks like when you do it yourself. We'll talk about what we're doing here in just a second. But you can see it's a little bit messier, but the benefits are pretty nice. So what's exactly happening? Let's highlight each part of this code and see what we're doing. So the first bit is how wide is your vector unit? How many floating points, can you fit in your vector? And so on my machine, that'd be 128 bits. So I got 4, right? Now we're going to say, give me an accumulator of zeros. That way I have my 4 lanes, and I'm adding all my floats there iteratively, continually. I can do 4 at a time. Now I have this upper bound. What if I'm multiplying or doing a dot product of things that have 17 elements? That's not divisible by 4, right? So I'm going to have a little bit at the end that I need to catch up on. That's what the loop bound gives me. Here I'm going to load up these float vectors, multiply them together, add them to the accumulator, reduce my lanes, and then I catch up on the tail. Now I was like, this looks really complicated. Raise your hand if you've written SIMD code in C and have to worry about handling this by yourself. Anybody done that before? I see no hands. I can tell you, it's a pain. It looks way worse than this. So this vector species gives me the ability to transfer this from CPU to CPU. It'll automatically handle bigger bit sizes if it's 256, 128, or 512. In C land or C++ land, I have to do if, pragma, def, and blah, blah, blah. Oh, it's horrible. So this is actually much cleaner. So is it actually worth it? So here's some benchmarks. We all like benchmarks. We all like statistics. They only lie to us sometimes, right? So this is a micro benchmark. The bigger number is better. So if you're just doing a straight up loop on a thing that has 256 bit size, you get 8 times the speed on throughput. So you say, everybody chuckled at how complicated that code looked, but you'd write that code if it got you 8 times the speed, right? So even in Lucene, where there's significant const overhead, we saw a significant bump in our nightly benchmarks. Elasticsearch, which uses Lucene, we had a significant bump that evening. Our benchmark people hit me up in Slack, was like, did we break something? It's like, no, we did not break anything. We just made it better. So don't worry about it. And here, this is a public benchmark for vector search engines. And that blue is what it was before, and the red is what it is now. And the thing that kind of blew me away was when I was reading this, is that this is better than some native implementations for different algorithms. So everybody's talking about how Java is slow, and I mean, come on. I mean, if we can beat C++, I mean, what else is there, right? I guess Rust. Don't worry, we could talk about Rust. But yeah, so was it worth it? I think so. That's my talk.